Cho cái mình sẽ coi ngay trước.
Em thì coi đất nước được, tôi cho vui vui thôi.
Đâu nhỉ?
Đây thì thuốc dưới là thuốc dưới. Representative.
So we start with the video.
Yes. This was the historical events for cosmology and astronomy in August 2017. It was this year.
Come up to
Well, but no video.
When we can go to the
YouTube, it was.
I download too.
Ah.
The no. So you can go to the Gmail.
No, YouTube.
You can find it on YouTube.
Yes. Reapers of gravity. Ezra.
For the first time, astronomers have detected a single cosmic cataclysm in both gravitational waves, ripples in space-time itself, and electromagnetic waves, what we typically call light. This hugely collaborative effort includes the LIGO and Virgo gravitational wave observatories, along with a multitude of telescopes in space and on Earth that, together, collectively monitor the full spectrum of light. The spectacular event was produced by the collision and merger of two neutron stars. These objects are the burnt-out remains of giant stars that have exploded as supernovae. They leave behind cores of exotic matter composed primarily of neutrons crushed together under the intense pull of gravity. More mass than our sun is compressed into a sphere that is about the size of a city. Astronomers have long known that neutron stars are found in pairs, orbiting one another. The theory of relativity predicts that the motions of these incredibly massive objects should generate gravitational waves. These waves would drain energy from the orbiting bodies, causing them to slowly spiral together and eventually collide with each other in a spectacular explosion. On August 17, 2017, a gravitational wave, CHIRP, was recorded by the National Science Foundation-funded LIGO observatories, and less than 2 seconds later, a short burst of gamma rays, a high-energy form of light, was detected by NASA's Fermi telescope. Researchers quickly realized these two fundamentally different types of waves could have come from a single neutron-star merger. If so, it was critical to identify exactly where this had taken place in the sky, and if the explosion could be seen by other telescopes. The Fermi data indicated the burst came somewhere from a patch of sky covering about 1,200 square degrees, an area equivalent to 6,000 full moons. Adding information from an independent gamma ray detection from the integral satellite, the search area was further reduced. The LIGO observatories placed the source somewhere in long, narrow strips of the sky, one of which overlapped with a target patch. The Virgo Gravitational Wave Observatory in Italy, working in conjunction with LIGO, should easily have been able to detect the signal at this strength, but saw almost nothing. This was an important piece of the puzzle, since any gravitational wave observatory has a small number of blind spots where it cannot detect an incoming signal. Restricting the source location to Virgo's blind spots further narrowed the search area down to approximately 28 square degrees, or 140 full moons. Around 50 candidate galaxies were identified in this area for follow-up observations using optical telescopes. Less than 11 hours after the first detections, astronomers using the Carnegie Swope telescope identified a previously unseen blip of light in the outer reaches of the galaxy named NGC 4993. Several independent confirmations were reported from other telescopes over the next hour. The first ever optical counterpart to a gravitational wave event had been found. Knowing exactly where to look, astronomers began an unprecedented campaign of follow-up observations using more than 70 telescopes around the world and in space. During the course of the next 2 weeks, the neutron-star merger was detected across the entire electromagnetic spectrum. The gravitational wave data have, for the first time, provided a direct measurement of the masses and orbits of a neutron-star pair before their collision and merger. The data also enabled ongoing follow-up observations across the electromagnetic spectrum, characterizing the explosion and revealing how such unimaginable events have played a formative role in shaping the world around us. These results, for the first time, confirm that neutron star mergers create precious elements like gold and platinum, as well as a host of other heavy elements all across the periodic table. Explosions like these, through our cosmic history, have seeded the universe with the materials that later will form new stars, new planets, and beings like ourselves who look up and wonder.
Yeah.
Trình bày đã được vỗ tay mình.
Cứ làm hết vỗ tay.
It's time for question. It's finished.
It's finished.
Okay, let's start.
So hello everyone, I will talk about my work as a research engineer on the LISA project. So I am optical instrumentation engineer and I have worked for 1 year now on this project. So my presentation will be not very, but will be more technical than So first I will introduce what is the space mission LISA. Then I will talk about what is Twilight. This is my subject. And my presentation is composed of two parts. In the first part I will talk about the general study of the telescope design before we fix the final design. In the second part I will talk about the telescope analysis. So we analyze the final design of the telescope, of the mission. So thanks to the video, I can skip the introduction. So LISA it's LISA, Virgo, LIGO is interferometers to detect gravitational waves. Gravitational waves are, as you saw, are ripples of space-time curvature. And it propagates with the speed of light and don't distort a lot. In the video you saw that there's two main projects of a brown interferometer. You have LIGO, the American. You have Hanford and Livingston. So and the Virgo at near Pise in Italy. And LIGO was the first to detect gravitational wave in the 15th of September 2015, and Virgo detect its first gravitational wave this year. I think the first is on June, not on August, with the big events in the video. So this is the frequency which frequency where LISA can detect this kind of frequency. And this is what where LIGO can where LIGO can detect events, cosmologic events. So this is the merger of black holes. You have the mass on unity of solar masses. This is gravitational wave, the 14th of September 2015. So you have this kind of LIGO. I think it's Livingston. So you have this kind of the gravitational waves was provoked by the merger of black holes with this kind of solar masses, and it formed a bigger black hole with this solar mass, this size. So what is LISA? LISA is a laser. It stands for Laser Interferometer Space Antenna, and it is composed by 3 satellites. Each satellite it's distant from the other satellites by 2.5 million kilometer, and they are linked by laser. LISA will be the first in space gravitational wave observatory. It is the mission. It is a mission large L3 of ESA Cosmic Vision. So it's a program from ESA. NASA is a junior partner. They quit a long time ago, but they come back this year because
after the Lego Olympic Book? After the Lego Olympic Book?
I don't know if I don't know exactly, but
I think
they yes. Because because of lack of money. So it will be launched in 2030 and 2034, we hope. So this year was the end of the phase 0, and next year on March we will be on phase A. So yes, you have 3 interferometers. You have two optical bench, 2 telescopes in each satellite, and this is it can measure delta L on L of 10 to minus 21, and Virgo can reach 10 to minus 22 now. So you have the spacecraft YVCA and the link. You have one laser, the transmitted beam, the received beam in each spacecraft, and this is linked like that. So yes, the received beam, the received beam, the transmitted beam to 2.5 million kilometers far, and you have telescope here. The same telescope here. They are identical, and this is the 2 optical benches. So the project I worked for is the ITT telescope, so Invitation Tender Telescope. It is a core mission from ESA, and so we work with Thales Alenia Space, which is the leader of the project. So you have ESA on the project, Thales Alenia Space, Cannes in France, and Torino. In RIM, which is an institute in Italy, Torino also. CNR, I think it is Spanish. OCA, l'Observatoire de la Côte d'Azur, at Nice. LMA, laboratoire de matériaux avancés at Lyon, and APC. LMA did all the mirrors on Virgo. They are I think in international, worldwide, the first. They are the best to do the coatings and so on the mirrors. So, in fact, we are a concurrent of NASA study. So, the NASA will do the real telescope, but if they quit again, our telescope will be the telescope used for that. But our study is not done for nothing, because there are some straight studies, for example, which can be used, but the real telescope is not
telescope.
NASA quit again.
Did you share the screen for the remote participants? But we can have solo the slide idea and the second screen.
Kéo qua một
kéo.
trái.
Kéo rồi không được.
Ở đây có thấy
Kéo nữa, bàn tay ra.
Không thấy.
Kéo lên, kéo xuống.
Rồi tắt hết ra rồi.
đó.
Đây, kéo lên.
Mình nhớ vẫn là phím nóng rồi.
Hay là kéo lên.
Không screen được à?
Dưới. Trái.
Thử rồi không được. Khi bao coi được máy nó như vậy. Nó dâu của Microsoft đóng vào còng Apple.
Tắt luôn.
Tắt đi bật lại. Nó chỉ có PDF.
Em có PDF.
Không thì lấy máy của anh.
Em cũng có máy của em luôn, nhưng mà không có. Tại anh mở vậy không được, không sao đúng không? Không thấy đâu. Hay là nó mở to.
Để mình đi. Xuống tên thì này. Này nhìn dễ hơn.
Nó vậy cũng được, không thấy.
Ok, sorry.
Chỗ đó.
Kết quả không, kết quả cái bên bàn ngồi,
Trái.
bên tay trái.
Mấy bên trái hay bên nào đây? Bên trên. Okay.
Thôi tự kéo.
Xuống rồi.
Nói.
Còn lại đi em.
So this is all the industrial and laboratories who work for the ITT telescope. So APC, we did the stellar simulations. In RIM is the Institute Italian who calculate the stellar intensity threshold. Thales and Space design the telescope and do all the mechanism studies. Also at Côte d'Azur, and they do some simulation, numerical simulations on stellite. They did some mechanical design and LMA. For the moment, they participate not all. They participate a little. I think they will do the coatings, and we yes, they spoke about the coating, polarization on coating. So, what is our objective on this stellite study? The problem we fear is that when you have the transmitted beam in this way, the transmitted beam, the source is on the detector position, and it will, this is telescope, this will be a stellite, back scatter light from the optics of the telescope, and the light comes back to the detector's position. And you have also the received beam from the far telescope, far satellites at 2.5 million kilometers. And this beam will go through the telescope, go to the detector position, and there are another local laser here, and there will be an interference with the received beam and the local laser here. And the problem is that the backscatter light from the transmitted beam has the same intensity than the received beam, and so it can interfere with the local laser here instead of the received beam, and so we have a fake signal. It's not the real signal. So this is the problem, and we have to estimate the intensity of scatter light to know if it will be a problem if the mission is above.
Can I have a question?
Yes.
Because in space, the satellite is not really stable.
Yes.
So how do you catch the satellite one beam from satellite two? Exactly, the laser beam is very small.
There is a lot of mechanism. They have a propulsor, I think, and they have some. They will integrate the jitter. They call the jitter is the error on the angle of the laser beam, but they are working on the mechanism, and for the moment is not fixed, but there will be propulsor, and they will be aligned in exactly the angle they want. And
exactly the main beam.
they will yes, they will it can move, and they will yes, they have some mechanism on the part, but it is a problem yes for that, and this is they are part of error, which is be in the taking account in the measurement.
Thank you.
Yeah. So what is stellite? Stellite is on what it light which doesn't come in the right way, in the way we want. For example, you have light coming from to this optics and go here, but you have the tubes here, and the lights can diffuse by optics or mechanics, and they diffuse on the tubes. In the past we don't want they to go to, and so they finish for the problem is when they finish on the detector, for example, and this light has a phase which is not the correct phase. They have another phase. They have an intensity which can muffle the signals. This is noise for us. So this is what is stellite. Diffracted light can also be stellite, considered as stellite. So you have the backscatter light with the optics, so can be interpreted on direct reflection, diffusion. We will look at the diffusion on our study. So the problem is that you can combine the main beams, what I explained, with the interference, and so to do that. First, some remind and definition of radiometry, which is very important on astrolight.